Okay, first thank Professor Yang Zhongqing and Professor Daniel Horst for their invitation, and also thanks for the organizers and very thoughtful arrangement and hospitality. And it's my first time to visit Korea, and I'm very glad to have a chance to visit the Korea Advanced Institute of Science Technology and the India and the Korea, and in fact I have some special feeling for the Korean people, because I grew up in Yanbian. It's a lot, 50% of people are Korean people. I have a lot of friends, originally from Korea, North Korea or maybe okay, South Korea, okay, and also I like the campus, beautiful campus and a beautiful city, okay, and I'm also glad that the first two talks are both on the SKT computation model, and they give a very nice and helpful survey on the global existence of the SKT model and numerical schemes. And so it's easy for me to save time to skip some. I will not talk about global existence and just talk about the theoretical results on the traveling waves and the pattern formation, okay? And the part of work is a joint work with Professor Weiming Ni and Xuefeng Wang and some of my doctoral students, okay? This is I'm sorry, this is a mistake. Outline, and here the two speakers introduce the background of this model. So here I needn't to talk more details about this model, okay? But anyway, I want to give some brief introduction on the formulation of the nonlinear diffusion, okay, the cross-diffusion, and also I want to give some brief introduction about the relation of the cross-diffusion and the chemotaxis mode, okay? And here, this is the cross-diffusion SKT computation model. And this is a nonlinear or quasi-linear cross-diffusion, and I'm sorry. Okay. And the nonlinear diffusion, for example, U species in this form, and there are these types of diffusion can be explained in two point of views. For example, if from macroscopic point of view, according to physical Fick's law, and here the diffusion, nonlinear cross-diffusion term, here JU is the flux, represent the dispersal flux. And here dispersal flux is the minus gradient of function S as a function U and V. And S is it's a bistable, it's a bilinear function U and V. And here, this type of dispersal flux means that the species U moves from the higher density of the SUV to the lower density of SUV due to the intra-population pressure and the inter-species population pressure. Okay, but from the microscopic point of view, we can see that the selection of transition probability of each individual species determines the form of the diffusion of species. For example, in the simplest case in one-dimensional space, if you consider the corresponding microscopic scale model, which is continuous in time, spatially discrete model, and here UI represent the population or probability of the species U at the position xi, and this is H, just a one-step model, okay? And here, this is the microscopic scale model, and here tau I is called the transition probability of individual species U per unit time for one step jump, and moving from the xi to the right neighboring site, okay? And the tau I minus means moving from xi to the neighboring left site, okay? In general, the transition probability can be a function of the UI, VI, and UI plus, VI plus. It means that determined by the population of the U, a starting point and the destination point. Okay, but for simple case, it's well known that when tau I is a constant, SI constant, then after passing some parabolic limit, the limiting model becomes the microscopic PDE model, which is just the classical reaction diffusion equation. Here, D is the random diffusion. Okay, and for the derivation of the SKT types of nonlinear diffusion model, if we select the transition probability in this form, if the transition probability moving from xi to the right side or to the left side, they are same. And just depending on the probability or the population, the two species at the starting point, in this form, it's a linear combination of U and V. And but for the species V, if this species is inactive, it's in this similar, but maybe different function. And then the transition probability of U, with this type of transition probability also means that the species U, the probability of species U depends only on the dissolved individual to leave the point. Or we can say the repelling force is proportional to the value of the population, this type of population at the starting point. So this is the explanation of the microscopic model of the SKT. Okay, and if we choose another type of transition probability for the species, which also can be considered as a strategy of dispersal species, may introduce some other forms of diffusion term. For example, if the transition probability to the right depends on the difference of the another species, and then which also means that the species U can detect the difference of the competing species or the another species before moving. Then, after taking limit, the microscopic PDE model of U and V becomes the typical KAIST chemotactic model with diffusion. So this is the KAIST chemotactic model. Here, just the difference is that, and the transition probability depends on difference. Okay, but for the SKT, doesn't depend on the difference, just depends on the starting point. Okay, the probability or the population of two species at the starting point, just depends on the desire of their living. Okay, and so this is SKT, so this is the KAIST model. And here, the minus gamma, this form is also called the chemotactic term. And the gamma is called the chemotactic sensitivity. And if gamma larger than 0, the cross-diffusion term is also called the positive taxis. Okay, but for the SKT model, we can see that this is cross-diffusion term, gamma Laplace UV. There's two terms. One term is gamma, there's a positive. So this is contains negative taxis, and this is an additional term. Okay, this is not the second cross diffusion, just the strongly coupled term. Okay, and I have to say, in recent 20 years, the SKT types cross diffusion model has received a lot of research interest. Okay, for mathematicians, and also there are a lot of various types of chemotactic models. And these two types of cross diffusion models have close relation, but they have some difference. And in the following, I shall just focus on the theoretical analysis on the SKT computation model with cross-diffusion, especially on the trailing waves and the steady state. And the trailing waves can explain some phenomena, wave phenomena, or invading of species. And the stability of existence of steady states may explain some pattern formation phenomena induced by the cross-diffusion. Okay, and we all know that without self-diffusion, cross-diffusion, the SKT computation model becomes the typical Lotka-Volterra computation model with diffusion. And for the logical-Volterra computation model with normal boundary condition has been widely and deeply investigated, and it's all know that the asymptotic behavior solution is nearly the same, except the strong computation case as that of logical-Volterra ordinary differential systems. Okay, any non-negative solution initial value. The solution with the non-negative initial value will tend to some constant steady state eventually, except strong computation case. And for the more general case, including the strong computation case, Kishimoto and Weinberger, and there is a well-known results. They show that when omega is convex, the logical-Volterra computation model with random diffusion has no stable non-constant steady state. And later, Matano, Mimura, Kanyang, and Nagida, they give some examples of some types of type non-convex omega, and they show that there exists stable non-constant pod state. Their results imply that the diffusion, if the domain is non-convex, for some non-convex domain, the diffusion may induce some new pattern formation. Okay. And now we consider for the logical-Volterra computation model in whole space, and consider the existence of stability traveling waves. There are a lot of work on the existence of several types of traveling fronts. Front means the monotone traveling waves. Here, I just consider the planar wave. Okay, so here the planar wave just can be written as a one-dimensional space. Okay, so this is the simplest case. For the classical Volterra computation model, there are a lot of work. And for example, this is the weak computation case, Tang and 5 obtained exit traveling front with infinite many speeds and connecting these two constant state. And this is the strong computation model. And also there are a lot of work on the traveling front connecting another two constant state with infinite speed. And for this case, when the parameter D1 is small enough, Hosono using analytic single product method can prove the exit traveling waves with transition layers. Okay, all these are the speed with have infinite many speed. And for the special case, strong computation case, this is a very interesting case. Gardner, Conley, and Kanyang, they use different methods, can obtain nearly the similar result on the distance stability of traveling waves, but this wave is with unique speed connecting these two semi-trivial steady, constant steady state. But the traveling wave connecting this semi-trivial constant state may explain some phenomena. For example, may explain the computation excludes principle. And here, the sign of the speed it may be very important, which may determine which species invades successfully or win at the end. For example, when C is larger than 0, the species V will win, and the C less than 0, the U species will win, and C equals 0, the two species will coexist. Okay, and the Gardner they prove this using theoretic method. They can prove the existence and the stability of the traveling front connecting these 2 points, two constant states. But here, say, it seems that there is no estimate on the sign of the C, not C star, just C. Now I consider the SKT model with cross-diffusion. Okay, so here I consider in this form here, U species, the diffusion rate may be very small, which means that the U species is inactive, but the V species has is active, and also the strategy is related with the cross-diffusion. Okay, and we can prove that for the strong computation case, when the cross-diffusion parameter is larger than some constant, then if epsilon is small enough, then there are traveling waves connecting these two semi-trivial steady states, and with a locally unique slow speed. C is in order of epsilon, and both components of V has a transition layer. And this is the profile of the traveling wave. Okay, and here I can when epsilon tends to 0, we can the slow speed has some estimate is in order epsilon, and the limit of C epsilon tends to constant C0, and the sign of C0 is the same as this integral. Okay, so here beta star is some special constant depending on the V species. Okay, anyway, for this special type of system, we can get some estimate on sign of C. In biological, maybe we can give some explanation. But anyway, I will not focus on the biological meaning. Okay, and this is for the SKT model with cross-diffusion. When one diffusion rate is very small, this is linear random diffusion. This is with a quasi-linear cross-diffusion, and the stability of traveling waves I can also prove by applying Evans function method, topological index method, which is related with computation of a Chen number, and also based on some argument of Chris Jones, Gardner's, their method, and we can prove that the traveling waves with transition layers is we obtained before is locally asymptotically stable with shift if the parameter epsilon is small enough. Okay, and I have to mention that it's very strange that for the strong computation case, if the cross-diffusion parameter is small, not larger than some constant, we don't know the existence of traveling waves connecting these 2 points. But for the case gamma equals 0, there are some well-known results. Gardner and Kanyang, they can prove existence and stability of traveling waves, but use the comparison method, but not it's a different method from ours. But for the gamma equals 0, gamma equals larger than 0, small enough, we don't know structure of wave. Okay, and here I have to say that the structure seems to be different from the case when epsilon very small. The transition layer, the structure of transition layer may be different, maybe more complicated. Okay, okay. Now I consider the degenerate SKT model. Okay, here if the U species diffuses in porous medium as case, okay, this is epsilon square U square. And we still take the strategy with cross-diffusion. And my student and I can using the analytic singular product method and the central manifold method. This is inspired by the Hosono's earlier work, 1987, and on the degenerate diffusion with different reaction terms, okay, classical reaction diffusion system. And for the strong computation case, if the cross-diffusion is large than some constant, and for small epsilon, we can also obtain these traveling waves connecting these two semi-trivial constant. Okay, and here the speed is also locally unique, and it's a slow speed. Okay, and we also get the estimate of the C epsilon, okay, tends to some constant. Here we need the assumption C star is non-zero. Okay, we can compute the sign of C star. Okay, and here the both component has transition layer. And here I say for some cases the component U may be weak traveling waves, and for the C star larger there the waves is smooth. Okay, but now for the similar to the non-degenerate case, for the case gamma 2 equals 0 or small enough, we don't know the existence, no results about stability. Okay, so that's the technical problem. Okay, and as for the SKT model, we are more interested in the pattern formation, okay, induced by the cross-diffusion. I mentioned that the work of Wimberger and Matano's work, they imply that for the classical local terror model, there is no new pattern induced by the diffusion. Okay, but now we are interested in if it's possible to get some new pattern formation, and just due to the appearing of the cross diffusion. Okay, so consider steady state of SKT model under the Neumann boundary condition, homogeneous Neumann boundary condition. Okay, there are a lot of work on the SKT model and the normal boundary condition. Also some work on the Dirichlet boundary condition. So a lot of work. Mimura and Nishimura, Tasei, Kayang, and Yuanlou, Weiming. And I shall introduce some of close related work later. And Kuto, Yamada using the bifurcation method and can get a lot of work on this model. Okay. Now consider, for simplicity, we consider a one-dimensional case. For one-dimensional case, there are a lot of work with more detailed information, okay? And this is the one-dimensional space with cross-diffusion. And the first results on the first theoretical work on the existence of steady state seems to due to Mimura, Nishiura, Tasei, and also, sorry, I didn't remember that. They proved the existence of positive steady states with interior and boundary transition layers. Okay, and for the cross-diffusion system, if D2, here D2 is small enough and D1 is large enough, but gamma 1 is larger than 1 under some abstract assumptions, okay, and covering some cases, okay, and they can prove that the existence of transition, here interior transition layers, the solution has a steady state has transition layers, okay. And Kayang, using the SLAM method, proved the stability or instability steady state. These two types, several types of steady state transition layers, under some additional, maybe under some additional some abstract assumptions, okay. Here not talked. Anyway, their work imply that the cross diffusion indeed induce some new pattern formation when the gamma 2 is large, when the cross diffusion parameter is large enough or not very small. I'm sorry. Okay. Now consider the existence of stability states with another type of structure, okay, especially spike layers. Okay, and Yuanlou and Weiming needs there are two important papers in JDE in 1996, 1999, and they obtained some very nice results about the existence and the non-existence of non-constant positive steady state solution. And their work also has some very interesting phenomena for the one-dimensional case, and they construct some positive steady states with boundary spike layers, okay, when one of cross-diffusion parameter gamma 1 is large enough. Okay, so their work may also imply that the cross-diffusion indeed induce some other new types of pattern formation. Okay. And this is one of their work on the in one-dimensional case when the gamma 1 is large enough and the ratio gamma 1 over D1 is both large enough and the random diffusion rate of species V is small enough, but no cross-diffusion parameter. And they proved under these two cases, one is a strong computation, another is weak computation, and some assumption, and they proved the existence of positive spiky steady states. And there, the spiky steady states, the height of the boundary layer are bounded, okay? But under this type of positive spiky steady state is near the positive constant U star V star, okay? Here can, and they also obtained other type of steady states near the semi-positive constant steady state, okay, A1 over B1 under this assumption, when A larger than B, okay? This capital A means A1 over A2, capital B means B1 over B2, okay? And here is similar, gamma 1, gamma 2 is here, the species we can be take the strategy with the cross-diffusion, but the D2 is very small, and D1 and gamma 1 over D2 both are very large enough, okay? And here U and V have bounded boundary spike layers. Okay, this is the cases 1 and 2. This spike is just near constant state, but the stay away from the 0 has especially the V, steady V has a lower bound, positive lower bound, okay? And for the cases 3, the spike is near the a semi-trivial constant state. But here, the height of V is very small. But here there's some problem. V is very small, but the height of U, the spike, is bounded. Okay. And to say that these two types of spiky states theoretically can be proved is unstable. Okay. And our work is can prove for case 1, case 2. Most of the cases, especially some parameter on some zero measure, and the spiky steady states near the positive constant are unstable. And also we can prove that for case 3, the small spiky steady states near this constant steady state is also unstable. And the method of proof of the instability for these 3 cases are using the spectral analysis for the 2 types of limiting system. And for case 1, 2, and case 3, the existence is obtained by constructing some solution based on the limiting system. The limiting system are different, 2 types of limiting system. So you consider the spectral analysis for the 2 types of limiting system, then get the detailed singular regular perturbation estimate based on the spiky structure of the steady state. And the spectral instability results are different for the 3 cases. And the existence of unstable eigenvalue for the shadow and near some positive numbers. For case 1, there's 2 unstable eigenvalues, and the case has 2. And for case 3, just only 1 unstable. But all these unstable eigenvalues are near the positive numbers. Okay. Okay, here I shall not talk the details about the proof. Okay, now consider the other types of spiky steady state. And in 2004, Lowney and Yatsutani, for the limiting system of the regional SKT model, when the cross-diffusion parameter gamma 1 tends to infinity, and the ratio gamma 1 over D1 tends to infinite. And it expected the solution, the steady state after selecting the sub-convergent subsequence, okay? And the solution seems to tend to the solution of this limiting system is also called the shadow system. So they consider the shadow system, and they consider using the elliptic function and obtain the nearly optimal and complete results on the existent, non-existent of monotone positive steady state. Here I shall list some important work. For example, the existent, non-existence. Okay, and for the parameter D2, the random diffusion rate of V, D2 is larger than this constant, then the shadow state has no positive non-constant solution. And under these assumptions, when D2 is less than A2 over pi square has some positive solution, and under this assumption, and the D2 is in this region has a positive solution, and all these solutions can be represented by elliptic functions. Okay, and I know that I learned that Professor Yatsutani recently obtained some uniqueness results about steady states. Okay, and also maybe some more interesting. And here I say that the results in 2 and 3 also imply that when D2 is small enough or less than some constant, then under these 2 cases, there exists a non-trivial positive steady state. And for this case, D2 is near this constant, okay, and also has there exists the states. For example, and for this special case, okay, A larger than this. And in their paper, they pointed that there is a very interesting phenomenon. There exists a special type of positive spiky steady state, which is not near the constant steady state for case 1, case 2, and for the shadow system. Okay, for example, D2 tends to 0, and they can prove that when D2 tends to 0, and tau tends to some constant, then the steady state component V has a boundary spike layer. Okay, x cross 0 satisfy this one, and this spike layer at x equals 0. Okay, and I can show the profile. This is V species, this is tau. Tau is it's not the component U, it's a combination of U and V after some transformation, okay? And here tau is expected to be the product U and the V as gamma 1 tends to infinity. This is the solution for the shadow system, okay? And in their paper, they expected or guessed that for the regional cross-diffusion system, when D2 is small enough, gamma 1 and gamma over D1 is large enough, there should exist some positive, large spiky steady state satisfying this property of this structure, okay? This is the up transformation. Return to the regional model, expected that the V, this is a spike layer, and U has a very large spike layer, and when gamma 1 tends to infinite, epsilon tends to infinite, then the magnitude, the spike height will tend to infinite. Okay, so this is another type of spiky steady state. And later, my student and I, Dr. Chen Xu, we can prove that their guess is correct, okay? And applying different approach. We use a special perturbation method. We can find the explicit approximation solution, and using some singular perturb method and some integral estimate, we can prove that we can get the detailed spiky structure of the spiky states for the shadow, and then we can get the existence of large spiky state for the night shadow. Here, just this is for the shadow system. The detailed structure can be written in this form. Here, this is the component tau. This is the first order, the same as Loney and Yazutani paper. And this is the second order approximation. This is the order epsilon. And this psi, this is first order, same. Then this is second order. Okay? And this is the remaining term is decaying in 1/0 epsilon, exponential 1/0 epsilon. Okay? And based on this detailed structure, we can prove that the existence of large spiky state for the regional cross-diffusion system. Okay? This is the expected results. Okay? We can prove theoretically. Okay? And this is the existence. Anyway, maybe you're more interested in the stability of this large spiky steady state for the shadow and the night shadow model. And there are some numerical simulation by Professor Yazutani on the eigenvalue problems, and their numerical simulation shows that the large spiky states should be stable. And our recent theoretical analysis with Professor Xuefeng Wang also can imply that the large spiky states are stable. They haven't finished the manuscript. There needs some, there are still some technical assumption. Okay. Anyway, there are some special difficulty in spectral analysis because there is the magnitude of spiky structure, spiky layer is very large. Okay, anyway, I shall not talk more details. And here we consider another case when D2 is near this positive constant and still return to this shadow system. And Loney and Yazutani's work imply that for this case A larger than B and there exists positive solution. This satisfies this special asymptotic behavior, very special, a strange structure. Okay, and when D2 tends to this critical point, then the component C and the psi tends to 0, and the ratio tends to some function. Okay, but later we can prove that obtain the multi-tail structure of steady state. Why we obtain because we want to prove that the regional cross-diffusion model, the steady state can be obtained from the structure of the steady state for the shadow system. Okay, so we obtain the multi-tail structure steady state for the shadow and apply the different method using the up transformation and some estimate based on Liav-Smith decomposition and some local bifurcation argument. Okay, but in fact it's not a bifurcation point. Okay, and this is our result about existence and detailed structure. Okay, here just like a bifurcation structure. Okay, but here S is larger than 0. s equals 0, this is not solution. But s less than 0, this has no biological meaning, but mathematically it's a solution. Okay. Okay, this is the estimate. Okay, this is for the shadow system, and here skip the proof. Okay, and the stability of positive steady state for the shadow, we can also prove that this type of non-trivial positive steady state near 0. Okay, and is asymptotically stable. Okay, for the shadow system. Okay, and the method proof is spectral analysis and the perturbation argument. And based on the Liam-Smith method and some argument closely related with the bifurcation theory. Okay, and after transformation, we can rewrite it as the problem with the bifurcation structure. Okay, and sorry, and here skip the proof. Okay, and anyway, we can also prove the existing positive steady state for the original cross-diffusion. Okay, this is expected results. Okay, and when the cross-diffusion rate is large enough, for the original cross-diffusion system, there exists the positive non-trivial steady state, and just described by the approximated by the shadow system. Okay, and this is the structure U and V. U has a spike layer. No, not spike. This is a special function. You can write the limiting profile of U, and V is near 0. And we can also prove the stability of positive steady state. Okay, under the same assumption. Okay, so anyway, we can see that when gamma 1, when the cross-diffusion parameter is very large, there appear some stable and positive steady states, and this state maybe have spike layer or have some special singular structure, and the method proof is for the cross-diffusion perturbation argument. Okay, and the stability also spectral perturbation argument. Okay, this is not regular perturbation but singular, but may depend on choosing a decomposition and some. Okay, and for the later and for higher dimension case and less than 4, low, ni, and Yazutani, and they obtained the similar results on the existing stability of shadow and non-shadow for D near the critical value for the higher dimension case. For n-dimension case, just our case, but they apply some simplified different argument. Okay. And there are a lot of open problems about the existence of steady states. Okay, but we just consider the existing stability of the steady state when D is very small or D is near this critical point. But no results about the existing positive steady for the regional cross-diffusion. Okay, for the shadow system, Low, Ni, and Yazutani, they obtain a nearly complete result for the limiting system. For the original cross-diffusion, we can just prove that their expectation correct when D2 is small and D is close. And the stability also, we just consider the D2 is near these 2 points. And when D2 is not small or not near this point, no results about the stability of steady state for the shadow and the non-shadow. And also, it's possible to have some other type of steady states in higher dimension and how about structure of non-trivial? But for higher dimension, the unique result is just Low, Ni, and Yazutani. They extended the result in one dimension or to the higher dimension. So there are a lot of open problems. Okay. Oh, thank you for your attention.